Cancel that.
So the interesting thing about mass in this question is that we don't need to know it. So that, I noticed they didn't give the mass in the question. So V in this case is 2gh square root. Which isn't that similar to some of the things that we did earlier in the semester? We used equations. I would say that's very similar to the equation that we can't see that's behind here, with 2g, 2 acceleration times delta theta. Anyway, conservation of energy shows us that the final velocity will be the square root of 2gh. So what is that in this question? 2 times 9.81. And what's h is 2.76 meters. So what's all that? So what's 2 times 9.81 times 2.76? 20. It's about 50. And then square root must be about 7, something like that. I think it's 7. But you're going to help me here. What's that? Don't forget your calculator. 7.35. 7.35, is it? So, 7.35. Okay, so other questions? Yeah. Mm-hmm.
Chapter 9, the main topic is like sticking versus like
Elastic and inelastic collisions, yeah.
those are the main power concepts.
Well, so chapter 9 was about momentum, wasn't it? So the big thing in momentum is conservation of momentum in a collision. So when objects collide, momentum is conserved if there are no external forces. So of course that wouldn't apply if you're giving it a push or something else, but I think most of the collisions that we've dealt with are just objects colliding freely with no external forces. So we use conservation of momentum. The big different categories were elastic and inelastic collisions. What's the difference between elastic and inelastic collisions? What's the difference? There's a difference physically and a difference in what equations we use.
One of them energy is conserved, one of them.
So the difference mathematically is that elastic collisions, kinetic energy is conserved. So elastic collisions are like billiard balls colliding on a table, right? Objects that can collide freely and don't stick together. Not only is momentum conserved, but kinetic energy is conserved. Inelastic collisions, what usually happens? They usually stick together, right? So the key, I think in all the questions that we had on collisions in chapter 9, wasn't there usually some key word in the question?
Yeah.
Or key words? It will say they stick together, or they don't stick together, or it says something like they move freely after the collision. So there's some clue in the question that tells you whether it's elastic or inelastic. Now, if it's elastic, then you can use those two equations, which I think I've got them summarized here. Remember, we got two equations here, these two equations here, which we derived. So I'll give these equations to you, so you don't have to memorize them. But after an elastic collision, the final velocity of the first object that comes in, the moving object, is this. And the final velocity of the second object, the one that's collided, that was at rest, is that. So the first object comes in m1. It collides with the second object m2. It's an elastic collision, so they move off freely. It's possible that m1 might even go backwards. This is the final velocity of m1. This is the final velocity of m2. See how this one could be negative, depending whether m1 is less than m2. So you would use those two equations. I'll give those to you, so you don't have to memorize them. I'll give them to you. But this is only for elastic, so it's really important that you appreciate that these are for elastic collisions. Let me just make that smaller. So head-on elastic collisions. Now, if they're not elastic, in which case they are They are typically they'll stick together. What equations can you use? You can only use conservation of momentum. So that was like the cars that have an accident. You know, remember the cars that were approaching, and they stick together and move off together. So you can't use these equations for that. You can only use conservation of momentum. So conservation of momentum is all that you can use for inelastic collisions. So you have to decide, when you read the question, do you think it's elastic or not? There's always some kind of a clue. So you know, we can do one of those if you want. But I want to try and keep this moving. I want to try and cover as many questions as we can. Yes?
Sorry, one more thing.
Mm-hmm.
General question.
Mm-hmm.
There is a difference between the forces between pushing and pulling, right?
Pushing and pulling. Well, the thing about pushing and pulling is that I think it was often to do with the normal force, wasn't it? So if I pull at an angle theta, then you would take the component. See, F cosine. So I pull the chair at an angle theta, right, to the horizontal. F cosine theta will give me the acceleration. And it's the same if I push as well. So it doesn't matter whether I'm going to go to the right. If I push the chair, F cosine theta will give me my MA. Right? Or if I pull the chair, F cosine theta is MA. But the difference is that pulling, then there's the F sine theta. F sine theta is the component that goes up. If I pull the chair, then won't that reduce the normal force? Because I'm providing a force in the upward direction. Whereas if I push the chair, that's going to increase the normal force. So if I push the chair, I'm pushing it into the ground, so the F sine theta goes into the ground, which increases the normal force. And then isn't friction proportional to the normal force? So I'm going to make the friction worse, if you like. I'm going to make the friction greater if I push. So if you want to pull a suitcase across the airport, it's more efficient to pull it, isn't it? Isn't it easier to pull the suitcase when you're running across the airport to catch your plane, rather than pull? I go like this. It took me years to work out it wasn't very efficient. But what's the most efficient way to pull your suitcase across the airport? It's to reduce the theta. If you can reduce theta to 0, that's the most efficient way. So, little children actually have an advantage because they tend to the theta tends to be quite small. It's actually quite helpful. But anyway, so I think that's the difference. The only difference between pushing and pulling is that it's changing the normal force, because you have to think about the direction of the F sine theta. So okay, so other questions.
Can you do chapter 6, part 3, number 6.105?
Okay, all right. And then what was your question at the back?
Chapter 8, part 2.
Okay, let me do this one first since we're on chapter 8. What do you say, 8? You say 8.2?
8, part 2, question 8.
And which homework was this in? Was this chapter 8?
Yeah, chapter 8, part 2.
Chapter 8, part 2. Yeah, let me just do this one first. Chapter 8, part 2. And which question number was it? Number 8. Is that 8.69? This is about a flea, is it? This is a flea jumping up and down? Is it about a flea? Yeah. Okay. So it says the flea. Yeah. Now there was a problem with the unit. I looked at the question here, and I actually made a complaint to Mastering Physics. They're going to change these units. This should be newtons per meter. They got the units wrong here. It says the flea has a force constant of 28. But that 28 should be newtons per meter. So I don't know if that's what confused you. So I sent them a message, and they're going to change it next time. So it just doesn't. The units were not correct. So now, when you jump, and it doesn't matter whether it's a flea or you. How is it that we're able to jump? I mean, how is it that we're able to actually lift ourselves off the ground?
Exerting that force to overcome gravity.
So essentially we compress energy into essentially you use our muscles as springs. Is that what it is? It's essentially the half kx squared. Essentially we compress spring and then we can release that energy into potential energy. So fleas are very good at this compared with their size. They must have a good force constant. So they're able to store a lot of energy when they compress their leg. So how high can it go? Well, it's going to be conservation of energy again, except this time, instead of being 1/2 mv squared, it's going to be 1/2, what is it? Not 1/2 mv squared, but 1/2. What's the energy stored in a spring? Kx squared. So when a spring is compressed, the energy that's stored is 1/2 kx squared. So make sure you look it up. Remember, I'll give you all these formulas on the exam, but you need to be able to know what to look up for. The energy stored in a spring is 1/2 kx squared. So you can think of the legs of the flea as being like springs. So they compress the spring, and they get this much energy compressed, and then when they jump, it gets released into mgh. Probably I should put it the other way around. If you want to do initial equals final, I should probably put it like that. So it stores all the energy as stored energy, then it releases into potential energy when it jumps up in the air. Now I think the thing about this